Hello students, welcome to the thrust of curiosity. Today we are going to see what is phase space and what are the phase trajectories. So consider a system of n number of particles. So they will have 3n position coordinates and 3n momentum coordinates. Like so for example, this is one particle or molecule. Q consists of x, y and z, and P consists of px, py and pz and so on. So for first particle we can write x1, y1, z1, x1, py1, pz1 and up to nth particles. So total we have 6n different coordinates, 3n position coordinates and 3n momentum coordinates, and all these coordinates are consisted in the phase space. So this is a 6-dimensional phase space we are working in. So this is a classical concept, but we are using this in statistical mechanics. We consider the smallest unit of this phase space is called as a phase cell. And so for normal volume, what we have? So for example, in 3-dimensional volume, we have d is equal to dx, dy, dz. Now because we have 6-dimensional volume, here we have dx, dpx, dy, dpy, dz, dpz. So this is the volume of a phase cell. And for very small particle, because these are having dimensions in 10⁻⁻10 meters or angstrom units or nanometer units, you can see. Therefore, we have the volume of this phase cell is equivalent. So this dx into dpx is considered to be equal to h cross. So this h cross into h cross into h cross is almost h cross raised to 3 or h cross cube. Now this we can also derive from uncertain relation. We are also aware of that. So from that also you can derive this. So this is the volume of a single phase cell. Now we consider this all things, all functions in the terms of P and Q, position and momentum coordinates. So suppose there is a Hamiltonian of that particular system, which is a function of Q and P, and consider because it is energy, let's say it is constant. So if this equation is satisfied by some locus of points in the phase space, we call it as a phase trajectory. We can solve this equation by these two canonical equations, and you also have seen this in classical mechanics. These are classical equations. So I have taken an example. This comes from harmonic oscillator case. Here Q0 and P0 are some constants which I have not mentioned here. This is not part of today's video. We can discover it later. So this is Q that depends on time, and this P is also depend on time. So you can see the square of sine square and cos square is equal to 1, but the constant is different. So therefore this is not a circle, but instead it is a ellipse. So you can see this is a phase trajectory. This is a phase trajectory. It also has arrows, but we are not concerned about this right now. Here you can see usually what we have x versus y axis. So on x axis we have all position coordinates. These all are position coordinates, while on the vertical axis, y axis, we have the momentum coordinates. So now we should not call x axis and y axis from now on, because position also itself contains x, y, z, all three axes, and here momentum contains px, py and pz. So each point is the locus, each point is the state of the system at some time t. So this is a phase trajectory. Now there are some questions in NET or state examination on this phase trajectory also. So you should remember that the two different phase trajectory will not intersect each other. So suppose this is the phase trajectory and I have some other phase trajectory like this. So this is usually not possible because the phase trajectories will not intersect with each other. Also, there is one more thing, that all phase trajectories must be continuous. So let's say this is the phase trajectory. So this is not complete phase trajectory. So this is also not possible most of the time. So we will see some examples discuss later on, and in that also we will discuss this later. Thank you for watching. Have a happy learning.